everyone, thank you so much for clicking onto the video. Today we're going to be looking at carboxylic acids, so here are the learning objectives. So first is to be able to identify the carboxylic acid functional group, and then to understand that hydrogen bonding affects the physical properties of carboxylic acids in relation to their boiling temperatures and solubility. And then we're going to understand that carboxylic acids can be prepared by the oxidation of alcohols or aldehydes and hydrolysis of nitriles. And then finally, we'll be able to understand the reactions of carboxylic acids with lithium tetrahydroaluminate, bases to produce salts, phosphorus 5-chloride, and alcohols in the presence of an acid catalyst. Now I'm going to introduce carboxylic acids. So the carboxylic acid functional group is this C double bond O, OH. And so it can only be found at the end of a carbon chain, and it has two functional groups, as you can see. So it's got the carbonyl group, which is the C double bond O, found in aldehydes and ketones, and it's also got the OH group found in alcohols. And this OH group is more acidic than the OH group in alcohols. And we name carboxylic acids by using the suffix enoic acid. So for example, for a carboxylic acid with two carbons, we call it ethanoic acid. And when we number the carbons, the carbon attached to the OH and the O is always labelled as number 1. That's the convention. And so the carboxylic acid group is always on the end. So for example, say we have a molecule that looks like this. So we've got CH3, CH2, CH2, and then C double bond O, OH. If we change this to carbon and then a methyl and a hydrogen, how we would label this would be the carbon with the double bond O and the OH would be carbon number 1 by convention, and that is always number 1. And so this would be number 2, number 3, and number 4. So we would name this 3-methyl because the methyl group is on the third carbon, and because there's 4 carbons in the main chain, so the longest chain, then it's a butanoic acid. Carboxylic acids can be formed from the oxidation of primary alcohols and aldehydes, as we've seen, and it can also be produced from the hydrolysis of nitriles. Carboxylic acids are also weak acids, and this is actually a really important point to remember. So they're weak acids, and so they're in equilibrium with their ions, as they do not fully dissociate. So the equilibrium that they have with their ions is not a straightforward reaction. So it's an equilibrium. And carboxylic acids react with alkalis, metals, and carbonates just like other acids do. They're just not as rapid. So now we're going to have a look at the physical properties of carboxylic acids. So first we're going to look at solubility. Now carboxylic acids up to butanoic acid are completely soluble in water, and this is because they can hydrogen bond with the water. So for example, if we had a look at ethanoic acid, so we have CH3, and then we have a carbon, a double bond O, and then OH. So we know that oxygen is a very, very electronegative atom, and so that means that we get some partial charges. So the oxygen gets a partial negative charge, whereas the carbon and hydrogen both get partially positive charges. And so what this means is that we can bond this hydrogen with the very electronegative atom of water, which is oxygen. So this is the hydrogen bond, and then we'll have the 2 lone pairs of electrons on the oxygen, and then we have the 2 hydrogens on the water. And again, this water has partial charges as well, so this oxygen is partially negative, whilst the hydrogens are partially positive. And so this is how we form the hydrogen bond between a really electronegative atom and a really not very electronegative atom. So hydrogen is not very electronegative, but the oxygen is very electronegative, and this is the hydrogen bond that we see. And one thing to notice is also that this angle here has to be 180 degrees. Another way that we can draw this is by bonding the hydrogen with the hydrogen of the water, with the oxygen in the double bond of the carboxylic acid. So for example, we have ethanoic acid, but this time we're bonding the oxygen instead of the hydrogen. And so again, we put in the partial charges. So we've got a partially negative charge here, whilst a partially positive charge here. And then we can form a hydrogen bond. And then we have the hydrogen, and then an oxygen, then another hydrogen. And remember that also this oxygen here has two lone pairs. So one of the lone pairs is what's hydrogen bonding. And then we have partial charges on these as well. And again, we have 180 degrees. So we can form hydrogen bonds between carboxylic acids and water in two different ways. The next thing we're going to talk about are their boiling points. So carboxylic acids can actually hydrogen bond to themselves in the solid state, and therefore they have much higher boiling points than their corresponding alkanes. And we can identify a carboxylic acid by measuring its melting point by using a field tube, which is a very accurate instrument to use for measuring melting points, and compare it to known values. And how it does this is, so looking at ethanoic acid again, we have CH3, C, and then double bond O, and then we have the OH. And again, we put in the partial charges, so we've got a partial negative here, and a partially positive, and a partially positive. And then we can draw a hydrogen bond to another ethanoic acid molecule. So we have 2 electrons, the oxygen, and this is double bonded to the carbon of this other ethanoic acid. And so we have CH3 and OH. And again, note that this angle here is 180 degrees. And it's because it can hydrogen bond with another carboxylic acid that it has a very high melting point, because hydrogen bonds are the strongest intermolecular force compared to in alkanes, where we just have van der Waals forces between the molecules. And again, we need to remember to put in the partial charges. And the third characteristic we're going to look at are their smells. So the smells of carboxylic acids are all characteristic. So for example, we have ethanoic acid, which smells of vinegar, and butanoic acid, which smells of rancid butter. So now we're going to look more into detail about reactions of carboxylic acids with metals and bases. And so we form salts, which we call carboxylates, when we react carboxylic acids with bases or metals. So for example, we could have sodium as the salt. So sodium will react with a carboxylic acid. So for example, we could have ethanoic acid, which is aqueous, and this will form a carboxylate. So we have a negative ion and then the sodium, and we call this sodium ethanoate. And we also form hydrogen gas, like we normally do when we add a metal and an acid. And what happens when we add a base with an acid is that, again, we form the salt because we're neutralizing. So, for example, we have sodium hydroxide added with ethanoic acid, and this will form, again, this sodium ethanoate, and also this time we're forming water. And we also need to balance the top equation. So we need 2 sodiums, 2 ethanoic acids, and 2 of these sodium ethanoates. And finally, the next example I'm going to do is with sodium carbonate. So we have sodium carbonate, which is also a base, and so it reacts the same way. So we have the ethanoic acid, and this goes to form, again, the sodium ethanoate. And this time we form carbon dioxide and water, like we normally do when we react a metal carbonate with an acid. And this balances by having 2 of these ethanoic acids, 2 of these sodium ethanoates. And how to name these carboxylate salts is that if we're using methanoic acid, then we use methanoate. If we use ethanoic acid, then we get ethanoate. And then propanoic acid is propanoate, and etc. So now we're going to have a look at the reduction of carboxylic acids. So we can reduce a carboxylic acid to a primary alcohol by using an oxidizing agent, such as lithium tetrahydroaluminate. And so the reagent we're using is this lithium tetrahydroaluminate in dry ether. And we're using room temperature and room pressure. So for example, if we look at propanoic acid, it has the formula CH3, CH2, and then you have the carbon with a double bond to the oxygen, and then OH. And we're going to add a reducing agent. So I'm going to note this by a square bracket and a H inside. And then what this will form will be the primary alcohol. So it'll be propan-1-ol, which has the formula CH3, CH2, CH2, and then OH. And then a really important thing to remember is that when we're reducing carboxylic acids, we always form water. And now we need to balance the equation. So on the left-hand side, we have 6 hydrogens, not including the reducing agent. And on the right, we have 10. And so that means we need 4 of this reducing agent. And this is how you'd set up an equation for the reduction of a carboxylic acid. So the 2 things to remember are that the first is that primary alcohol is always produced when we reduce a carboxylic acid. And it's either a primary alcohol or an aldehyde, but in this case we're doing it to a primary alcohol. If we were doing it to an aldehyde, we would have CH3, CH2, C double bond O, OH. So again we have propanoic acid, and we'd reduce this to propanol. So we'd have CH3, CH2, and then C double bond O, and again we get the water. And so to balance this, we have 6 hydrogens on the left, and we have 8 on the right, and so we only need 2 of this reducing agent, which makes sense because we're not reducing it the complete way to a primary alcohol, we're only reducing it up to an aldehyde. So we need to remember that carboxylic acids can be reduced to aldehydes and then to primary alcohols, and we have to use lithium tetrahydroaluminate, and we always form this water at the end. Now we're going to have a look at the reaction with phosphorus chloride. So the reaction between carboxylic acids and this phosphorus chloride form acyl chlorides, and these can be used in acylation reactions, which we'll look at a bit later. And also this reaction can be used as a test for carboxylic acids as misty fumes of HCl are produced. So the reagent we're using is this phosphorus chloride, and we're using room temperature. So we're going to look at ethanoic acid as an example. So we have ethanoic acid, which is CH3, C double bond O, and then OH, and we're adding this PCl5. And so we form this acyl chloride, which we call ethanoyl chloride. So CH3, C double bond O, Cl. So basically, the OH has been substituted by a chlorine. So we call this ethanoyl chloride. So acyl chlorides will come up in the topic of acylation. And then we also form POCl3 and also the HCl, which is the misty fumes. So now we're going to talk about esterification. Esterification is basically just when we react a carboxylic acid and an alcohol in the presence of a strong acid catalyst to form an ester. So for example, we can have ethanoic acid. So we have CH3, C double bond O, OH, and then if we add it with, let's say, methanol, we have COH and a hydrogen and another 2 hydrogens, and this will form the ester. So again, we look at the acid first. So we have CH3 and then C double bond O and then stop, and look at the alcohol. So we complete it by having a CH3. And we also get water because we're removing some water from it. And this is in the presence of a strong acid catalyst. So from ethanoic acid, and methanol, we have formed methyl ethanoate and also water. And this reaction is in equilibrium, and it needs an acid catalyst for it to occur. So in the equilibrium, we have a carboxylic acid, reacting with an alcohol, and this is to form the ester and also water.